Property 3. The complement rule for conditional probability. Welcome, everyone. Today, we are moving on to our third property, the complement rule for conditional probability. Before we dive into the new formula, let's quickly recap what we've learned so far. In our previous lessons, we established a fundamental idea. When we are given that an event F has already occurred, we are no longer looking at the entire universe of possibilities. Instead, our sample space effectively shrinks from the original sample space, which we call S, down to just the event F. Now, why is this important for today's topic? Because this shrinking effect allows us to take the standard concept of complements, which you already know from basic probability, and apply it directly within this new, reduced sample space. Essentially, we are going to learn how to find the probability of something not happening, but specifically within the context of event F. Understanding the concept. To understand this, let's start with something you already know from basic probability, the complement rule. You'll remember that the probability of an event E not occurring, which we denote as P of E prime, is simply 1 minus the probability of E. It's a fundamental rule that covers everything in our original sample space. Now, when we introduce a condition, like event F, the core logic of that rule doesn't change, but the scope does. We are now applying that logic specifically to the outcomes that fall within the new, reduced sample space of F. Think about it this way. If we are certain that event F has already occurred, then we are only looking at the world inside F within this specific context. There are only two possibilities for event E. Either E happens, or its complement, E prime, happens. There is no third option. Because these two outcomes cover every single possibility within our new space, the sum of the conditional probability of E and the conditional probability of E prime must equal exactly 1. As we are about to see in the next slide, we can actually use this logical certainty to mathematically derive the formula we'll be using for our calculations. Now that we've established how the sample space shrinks when an event F occurs, let's dive deeper into the concept behind this property. Mathematical derivation. Now that we understand the intuition behind why the complement rule works within a reduced sample space, let's look at the formal mathematical derivation. This slide will show you exactly how we move from the basic idea of a certain event to the specific formula we'll be using in our upcoming examples. First, let's start with the certainty of our sample space. As we touched upon in Property 1, once we are given that event F has already occurred, we are no longer looking at the entire universe of possibilities, but only at the outcomes within F. Therefore, the probability of the entire sample space, S, occurring, given that F has occurred, is equal to 1. In notation, that is, the probability of S given F equals 1. Second, we use the concept of decomposition. We know from basic probability that any event E and its complement, E prime, are like two pieces of a puzzle that, when put together, form the entire sample space. S mathematically, we express this as S equals E union E prime. Third, we apply our condition to this relationship. Since we established that the probability of the sample and space S given F is 1, we can substitute our decomposed parts into that expression. This gives us the probability of E union E prime, given F, equals 1. Fourth, we apply the addition rule. Because event E and event E prime are mutually exclusive, meaning they cannot happen at the same time, their intersection is empty. When events are disjoint like this, the addition rule for conditional probability tells us that the probability of one or the other occurring is simply the sum of their individual conditional probabilities. So, the probability of E given F plus the probability of E prime given F equals 1. Finally, we reach our destination, the final formula. By simply using basic algebra to rearrange the equation, subtracting the probability of E given F from both sides, we arrive at the complement rule for conditional probability. This is written as the probability of E prime given F equals 1 minus the probability of E given F. As you can see, the logic is a direct extension of what we already know, just applied within the context of event F. Keep this formula in mind, because in the next slide, we are going to apply it to a real-world quality control scenario. Real-world example. Now that we have seen the mathematical derivation of the rule, let's move from theory to non-practice with a real-world example. Imagine a quality control manager at a smartphone factory inspecting a new batch of phones. He has some specific information. He knows that a certain percentage of these phones are produced by machine A. We will call this event F now. Within this specific group of phones from machine A, some will be defective. Let's call this event E, and the rest will be non-defect, which is our complement, event E prime. Here is the problem. Suppose the probability that a phone is defective, given that it was produced by machine A, is 0.05. Based on this, what is the probability that a phone is non-defective, given it was produced by machine A? Let's walk through the solution step by step. First, step 1, we need to clearly identify our events. As I mentioned, let F represent the event that the phone was produced by machine, A let E represent the event that the phone is defective, and E prime represents the event that the phone is non-defective. Step 2, next, we identify the probability we already know. From the problem statement, the probability of E, given F, is equal to 0.05. Step 3, now we apply the complement rule we just learned in the previous slide. We are looking for the probability of E prime, given F. To find this, we use our formula. The probability of E prime, given F, equals 1 minus the probability of E, given F. Step 4, finally, we perform the calculation. We take 1 and subtract 0.05, which leaves us with 0.95. So to conclude, the probability that a phone is non-defective, given it was produced by machine A, is 0.95. As we move to our final slides, keep in mind how the condition F remained exactly the same on both sides of our equation. Key takeaways. First, it is important to remember that the complement rule for conditional probability isn't a brand new concept you have to memorize from scratch. Rather, it is a direct extension of the standard complement rule we learned in basic probability. The only difference is that we are applying it specifically to that reduced sample space we discussed in our very first slide, the space where event F has already occurred. Second, let's look at the practical application of the formula. The formula, which is read as the probability of E prime, given F, equals 1 minus the probability of E, given F, is your go-to tool when you already know the probability of an event occurring under a specific condition, and you want to find the probability of that same event not occurring under that exact same condition. Finally, a crucial point to keep in mind for your exams. The condition, represented by the vertical bar and F, must remain constant on both sides of the equation. You are not changing the context or the condition. You are simply switching from looking at the occurrence of the event to its non-occurrence. Now that we have worked through the derivation and seen how this applies to a real-world quality control scenario, let's pause and summarize the key takeaways from this property. Before we wrap up, I want to highlight a few common pitfalls to avoid, such as confusing the complement of the event with the complement of the condition, which we will cover in the next slide. Common mistakes. First, let's look at the danger of confusing the complement of the event with the complement of the condition. You might see something like the probability of E prime, given F, and mistakenly think it is the same as the probability of E, given F prime. Please be very careful here. When we write the probability of E prime, given F, we are text talking about the probability that event E does not happen, specifically within the context that event F has already occurred. On the other hand, the probability of E, given F prime, refers to the probability that event E happens, given that event F did not occur. As we saw in our smartphone factory example, the outcome changes entirely depending on whether the condition is met or not. These two values are generally completely different, so always check which part of the notation is being complemented. Second, a very common mistake is forgetting the condition entirely. Some students, when trying to find the probability of E prime, given F, will simply calculate 1 minus the probability of E. This is incorrect. As we discussed in our derivation on slide 3, calculating 1 minus the probability of E only gives you the unconditional probability of E prime. This ignores the extra information provided by event F, which effectively shrinks our sample space. To get the correct answer, you must ensure that the condition, the vertical bar F, remains present on both sides of your subtraction. Always remember, the condition stays constant. Now, before we wrap up today's lesson, I want to pause and highlight two very common pitfalls that students often encounter when working with the complement rule for conditional probability. It is crucial to keep these in mind to avoid losing marks on your exams. If you can avoid these two errors, you will have a much stronger grasp of how to apply this rule accurately.